Professor Subramaniam, for such a fantastic talk.
Sorry,
You have nearly 71 questions. Keep growing in your Q&A box. You can click the icon now. A window will pop up. Are you able to see that?
Yeah, sure. Yes. So shall I
you
go
can,
one?
Yeah, you can actually go the way or the order you want, and the question you think are interesting one to answer.
Okay.
And
so
if you find a name, you can cite the name of the person and then like read the question, because not all attendee can see the question. So please read the question and then answer.
Yeah, sure. So, thanks for this questions 79 as I can see it. So Srinivasan asked, is it fine if we have energy in our shirt because we may lose our privacy if we have any kind of miniaturization of devices? So this energy storage device, to answer very briefly, the energy storage device is all it's going to do is deliver energy to enable your sensor or another kind of active component to work. It could be a Bluetooth, in which case there is going to be data information, data transfer from your shirt to a device. But as far as I can see, it's all ultimately controlled from your end. If you don't want it, you can always switch off your Bluetooth, and then your energy is only going to be used to power the active component. So I don't see any kind of privacy problems with this. And can wearable storage, Shashi Kumar asked, can wearable storage device need printing? No, absolutely need printing technology. So both the devices that we have demonstrated in the talk absolutely does not need any kind of printing technology, any kind of lithographic platform. It can be mass produced, and that's a very key important advantage. Okay, and how can it be? Manas Ranjan asked, how can it be washable? Because the way we have put it, we have encapsulated with PET sheets. We have done this lamination process, and so that basically protects it from any external environmental conditions. So even if you put it in washing machine, soak it in water, add detergents, nothing is going to penetrate this PET packaging. So the packaging is what makes it washable and wearable and mechanically resilient. What is the advantage of lithium-ion batteries? Dr. R. Ravishankar asked. Okay, so this is something which I didn't stress too much in my talk. See, lithium-ion batteries. If you remember about the explanation about energy density and power density, lithium-ion batteries are basically Faraday systems. They are electron transfer systems. They can store a large amount of energy, but they are not very highly suited for power delivery operations. Whenever there is high power requirement, lithium-ion batteries actually the current industrial standard of lithium-ion batteries actually do not do a good job. So they are poor in power density, whereas supercapacitors are exactly opposite. Their energy density is minimal, but then the power density is very high. So Satadru, sir, thank you for your talk. I wanted to know what is your view on layered metal borides being utilized as potential supercapacitor. There has been an enormous amount of material research that has gone into supercapacitor candidates. MXenes have been very, very hot in MXenes or layered transition metal carbides and nitrates. Transition metal, basically titanium nitride, titanium carbides, and vanadium nitride, vanadium carbide. These are all layered materials which are showing enormous amount of potential as supercapacitor material. But one of the things which if you want to design a supercapacitor is that don't look only for surface area, look for porosity along with surface area. That is the balance of porosity and surface area, and rather accessible surface area is the key point to keep in mind when you design supercapacitors. Ian Day asked, what are influencing factors for area trapped in the CV curve? It's the dielectric, the ionic mobility, which is basically measured in case of solid electrolytes. You can quantify it by ionic conductivity of the electrolyte, the flexibility, and in our case, the flexibility of the device, the voltage range at which you scan, whether you can go to 1 volt or 2 volts or 3 volts. As you broaden the voltage range, naturally the area under the curve broadens, so your energy density is going to increase. So these are all the why did charge and mass transfer required for 2 electrode systems? So this Shashi Kumar asked, why did charge and mass? So charge and mass transfer requirements for the 2 electrode systems is more important in case of intercalation type systems, which are mainly batteries. In here, supercapacitors, we essentially want to balance the two double layer processes. That is what is important. Sushant Patil asked how to choose concentration of electrolytes in electrochemical measurements. Concentrations of electrolytes in at least through supercapacitor kind of systems should be chosen in such a way that there is minimal amount of Faradic processes happening. So that means should not be any charge transfer process that happens in the system. So whenever your electrolyte concentration becomes beyond a certain point, then there is a greater chance of Faradic charge transfer between the electrode and electrolyte, and that is actually going to degrade your supercapacitive systems. It might be good for other energy storage systems like batteries or ion capacitors, but in this case, it's not suited. Anonymous ask, could graphene be a substitute for carbon nanotubes? Absolutely yes. No, you can think of it. So you can do the entire story over again with graphene. Absolutely possible. Aishi Mitra said, you told no electron transfer is taking place between the metal and electrolyte in supercapacitor. If there is no electron transfer, then how do we measure CV? So what we do, when I said there is no electron transfer, what happens is if you apply a polarity, certain polarity to the metal, to the electrode side, then ions of opposite polarity from the electrolyte come to the interface, reside to the interface in an attempt to neutralize these excess charges which are lying on the surface. So that is essentially what is driving the formation of electrical double layer. So this electrical double layer is essentially the electrical energy that we pump into the system. The energy in terms of potential difference that we pump into the system goes to form the electrical double layer at the interface. And so that is what it's stored as. The energy is stored as in the form of electrical double layer. Hope I'm able to answer your question. So that's why when you don't have electron transfer, so you don't see any redox behavior. The CV is the cyclic voltammogram is absolutely featureless. It's basically a rectangle, square shaped or a rectangular shaped symmetric curve. Korak asks, is synthesis of carbon nanostructures or other shapes possible, and if so, how properties of energy storage device differ? Yes, there is a lot of shapes of carbon structures, non-carbon structures which have been reported, and energy densities basically energy storage properties differ purely based on the accessibility of the surface area and the electrical conductivity. With Dr. Anand Burange asked, without Raman, is it possible to distinguish between SWCNTs and multi-wall from TEP? Kindly elaborate. So yes, TEMs do give you a you will be able to essentially distinguish between single wall and multi wall using TEM by if you have basically multi wall nanotubes are multi-layered structure, Russian doll-like structure, like cylinder within a cylinder within a cylinder. So in that case, when you look at it through TEM, you would see multiple graphitic planes, and so if you have you can also do electron diffraction to distinguish between this, because multi-walls would be able to would be able to give you the graphitic plane, the diffraction pattern corresponding to graphitic plane. But the easiest, but remember, when you do TEM, it's only for a few tubes or a few very small portion of the sample at a given point of time. Whereas Raman, you can quickly scan the entire range, much larger sample, much larger statistics of the samples can be estimated, and so therefore Raman is much more preferred to distinguish between single and multi-wall. Okay. Naveen Kumar, hi Naveen Kumar. He asked, what is the criteria to choose surfactant to stabilize CNTs? Oh, this is something which I didn't elaborate. This for everything that so when you say that oil doesn't dissolve in water, or oil is invisible with water, it's basically to do with what is called as cohesive energy. The energy which binds to oil molecules together and the energy which binds to water molecules together are not the same. That's why oil prefers to remain with another molecule of oil, whereas water prefers to remain. This is what is measured as solubility parameter. Okay, so now when we design surfactants, we need to look at solubility parameters. Basically, it's a collection of all several cohesive energy terms. And so when we try to look for surfactants for stabilization or making dispersions, we essentially play around with the solubility parameter values and try to make them as close to each other as possible, and then you would be having better dispersions. Shashi Kumar asked, can we use Ctap for multi-wall nanotube stabilization? Yes, we can use Ctap, but there are problems for using Ctap. The stability is not that good, and there is also a problem of removing the Ctap after when you don't want it. Okay, so I'll probably skip a few slides. Then there are 150 questions. Arjun Ajit Mohan asked, hi sir, I had a few clarifications regarding CNT growth. Is there a lower limit for the length of the CNTs? A lower limit is basically you can make it as small as possible, but then longer is better in these cases, because with longer CNTs you would essentially be it would be easier to achieve percolation. So your electrical for the same weight of CNT, suppose you take 1 gram of very small CNTs and 1 gram of very long CNTs, then with 1 gram of long CNTs you can basically connect 2 points which are much farther apart. That is essentially what percolation talks about. So it's for those reasons it's better to work with longer CNTs, and that's one of the key advantages that we have. We can make it up to about 0.5 millimeters in length. Was the bending and the folding of nanotubes performed at? We didn't bend the nanotubes at nanometer level. We immobilized it on the CNT thread, and then we bent and fold or twisted the CNT thread. So that was done in a microscopic or macroscopic range. We didn't bend individual single nanotubes. What was Agnishwar asked, what about the stability and durability of the coated thread? We have done enormous amount of measurements to understand, to show to look at the stability and durability. We have done, like I showed you, some of the tests which I showed you, hammering, bending, twisting, washing. Nothing ever happens to the stability of the coated thread. So that's an important point. CNT adherence, Anonymous asks, CNT adherence to cellulose thread is a simple physisorption or some sort of chemisorption. We have done infrared spectroscopy and surface analysis. We do see that there is some sort of chemisorption which is happening between the CNTs and the cellulose platform. What were the difficulties you faced? I would prefer to skip a few more questions. Can you please comment on toxicity of CNTs towards skin, as the thread would be in contact with skin? Yes, CNTs by themselves are toxic to a certain extent when inhaled directly through breath, just like how coronavirus, when you inhale it, it's a problem. But here, because we are packaging the device between PET sheets, there is no way that the CNT is going to get in touch with the directly with the thread, with the skin or any other human interface. So therefore, absolutely no worry of toxicity. Ajay or Diksha, just tell me when to stop. Otherwise, I'll just keep scrolling down, and I'm fine.
Yeah. If you're okay, you can take a few more questions.
Yeah, absolutely. I'm fine. I can go on for another even till the end of this 160 questions. I can go on. So you just tell me when to stop.
Yeah, you may take few questions like next 15 minutes. That would be fine.
Yeah. Okay, perfect. So I'll try to answer as many as possible in the next 15 minutes. Dr. Jyoti asked, what is the best CNT, single, multi, double wall, for preparing conductive coatings on fabrics? See, this is a very kind of a I don't have a good answer for this, mainly because there is no correct answer. Okay, so it depends on the kind of application that you want, the kind of fabric. Say, for example, there is a difference. We can't use the same dispersion to coat a polyester fabric. The chemistry has to be different. So what is the fabric? What is the application that you're targeting? Whether you're looking for surface area or whether you're looking for conductivity of the coat after you coat it, all these determine what kind of CNTs to take. So CNT is basically, trying to imagine the CNT as a kind of a shop. You can go in and pick a lot of different types of CNTs, but what you would require is basically controlled by what you are trying to do with them. Okay. Can you clearly tell about IR drop in GCD curve, sir? Okay, so Gautam Babu Velingiri. So when you try to charge and discharge the device at constant currents, you basically ramp up the voltage as you in a constant current mode. You ramp up the voltage, and then that is the charging process for the device. Now, the minute you release the charging process, and you try to now that this charging process is when you try to the electrical double layer forms within the device. Now, when you stop the charging process and try to extract current, the double layer recombines within the electrolyte, and then that charge imbalance is what is manifested as current through the external circuit. So now that charge imbalance goes through an initial IR drop, which is called a resistive drop, before the actual discharge process starts. Now, this magnitude of IR drop depends on a lot of parameters, such as the mobility of the ions, the ionic conductivity of the electrolyte, as well as the electrode-electrolyte interface. So these are things which you should optimize to minimize the IR drop, because essentially the IR drop is the fraction of energy that you have already supplied, which is not available to you to take back. Okay, so that's why you should kind of try to minimize it. Okay, in parallel combination, the CV current is not symmetrical, whereas more units are connected. Please explain. I don't remember where you got that idea from. In parallel combination, also the CV curves are symmetric. Let me just go back to that slide. Yeah, so here the CV curves, if you see in parallel combination, this is just one capacitor, the red one. If I connect two capacitors in parallel, then you get the green curve, which means that this is also symmetric, but you can extend, because you have extended the voltage, you can now work up to work at 2 volts instead of rather 1 volt. You are not restricted by the voltage. You can go to higher voltage, therefore the current falls down. So that's I'm not sure where you got the idea from. It's absolutely symmetric. You can see the magnitudes of current and the shape and things like that. It's exactly how it's supposed to be. So I would need a little bit of input from your side as to where you got that idea. Okay, so Manas Kumar Kundu, hi sir, good afternoon. If you are using ionic liquid, why you are charging for 0.9 volts for a single cell? Is it water contaminated? Some cases, ionic liquids, most of the ionic liquids are hygroscopic, so we need to be very careful about avoiding water contamination. But as you can see from this slide, we have run experiments which can go up to 4 volts as well, higher voltages also. So without having seen a lot of Faraday content. But when we try to do room temperature ambient condition measurements, we need to be very aware of the water content in the ambience, because ionic liquids are going to be hygroscopic. Rahul asks, what are the different types of energy harvesting systems? Which mechanisms do you suggest? Yeah, you have given the answer here. Piezoelectric, electrostatic, electromagnetic, magnetostrictive, thermoelectric, just by utilizing the temperature of your skin, thermoelectrics. There is a new form of energy storage device, energy harvesters, which are called TENGs. These are triboelectric nano generators. You might want to check that out as well. Jinsey Thomas, once we will fabricate this type system, so what about its maintenance and disposability? You don't have to maintain it at all. You can put it, you can practically do anything that you do to a shirt with these kind of systems. So the disposability, because it's again a good thing, because it's again a carbon-based system, so you don't basically need to worry about environmental contamination. You throw it into the atmosphere, it is biodegradable. You throw it into the environment rather, it's biodegradable. What is the size of the device for specific amount of energy? So Manas Ranjan asks. So because each junction here stores energy, you can basically make hundreds and thousands of junctions and develop into a patch. And so that's why I always refer to the energy density and power density in terms of kilograms, normalized to the kilogram. If you can see this, it's basically, you can scale it from say about 3 kilowatt per kilogram in terms of power density and about 30 watt-hour per kilogram in terms of energy density. This is the lower limit. The higher limit, you can go up to 50 watt-hour per kilogram in terms of energy density. So that's quite a lot for the applications that we're targeting. So I'll just scroll. Okay, anonymous attendee. What are the experimental conditions? AC amplitude, AC voltage. I would request you to kindly look at these papers. These will have the exact conditions, and it should not show any charge transfer. What is the origin of the semicircle? The semicircle is basically the Warburg component, which comes in the lower, the higher frequency regime. Yeah, so that's the thing. Venkatachalam asked, what type of battery has longer lifetime with efficiency? That is something, if you want to, if you're looking for just cyclability, supercapacitors are far more cyclable than Faraday battery systems. Composite like multiferroelectric material can be used. If you're looking for supercapacitors, which are basically non-Faraday systems, I would think that these systems, multiferroelectric materials, would be better for pseudo-capacitive or Faraday energy systems. So try to think in that direction. So I'll try to see if there are. I'll scroll down a few things. Okay. Can you give me a bit idea about how CNT plus polymer gives this adhesive property? What kind of polymer can be used for this purpose? We have not used any polymer. We have used a surfactant to stabilize the CNT and then later remove the surfactant. So there is no, we are working with pure CNTs. Shana asked, when you CNT threads are fluid in the polymer electrolyte, the parallel position between the two CNT electrodes are very low. For example, the interaction point between the two lines is a plus symbol. There's only a point which is very low when compared to the length of the line. Yes, so what we did show you, for example, this slide shows you is that these are junctions, but now the remaining part of the thread is unused. We have just wantedly left it unused. You can create as many junctions as possible. Like, for example, the way we showed here, we can create. Oops, sorry. If you see here the horizontal tunability, you can create n number of junctions. This is completely easy to scale it up. You are just increasing the area over which the threads are sewed. So it's very easy to scale it up in that fashion. So that's the reason. That's the advantage of using these junctions. The other advantage is that even if one junction fails, that single junction alone is going to fail. The rest of the junctions are not going to get affected, and so the rest of the junctions are still going to continue and store energy. That's a very important advantage when it comes to parallel junctions. So when you have parallel, you touch at any point, then the entire device fails. It shorts and the entire device fails. Whereas when you have junction, even if this junction fails, the working of the adjacent junction is completely decoupled. So that's an advantage. In case of wearable device, yeah, I think I've answered this question before. What is the effect of drawing ratio on the conductivity of the CNT? The drawing parameters are very crucial. I would recommend you to look at the paper. The rates, everything is mentioned there. Okay, is the conductivity of the coaxial depends on its dimension? Yes, to a certain extent, yes. The conductivity does depend on dimension. What is Kaushik Ghosh asked, what is the thickness of the? Hey, hi Kaushik. If I think you are from INST, Kaushik. Hi. What is the thickness of PVA sulfuric acid? So we have played around with the PVA sulfuric acid thickness. For the best devices, I think you are referring to the coaxial one. So for the best devices, we get something like 150 micron is the thickness that we utilize. That seems to be the optimum. And is it? I can't understand the next question. How does the performance of depends on thickness? Yes, so Sudeep also asked the same question, that the thickness of the electrolyte sheet. So basically, if you make it too thick, then the ionic conductivity in that direction is going to get lower and lower. So that means there is going to be more and more less and less of electrical double layer formation. At the same time, if you make it too thin, then you run the risk of shorting the devices. So this has to be maintained at an optimal thickness. So that's something around 150 microns is what we have worked out. Kaushik again asked how the distance varies between two conductive electrodes in two devices like stitching threads and coaxial electrodes. So more or less the distance is same, roughly the same. Yes, because the thickness of the electrolyte is exactly the same. So what does annealing do to the anonymous asks what does annealing do to the yarn that makes it more supercapacitive? Any experiments that we have done a lot of experiments. I was not unfortunately able to elaborate much on this so one of the things which I showed you is the Raman spectral mapping. So basically the annealing helps to make create that diffuse layer of the interface. If you see that there are two distinct components, one pertaining to the CNT, another in the electrolyte before the annealing. The same junction, once you anneal it, you see that now the electrolyte has infiltrated the electrode. That means you are establishing more of the electrode-electrolyte interfacial area, and that is important, and that is why the capacitive nature increases and the scantrate capability increases. And then things millivolts per second in the slide. No, Manas, I wanted to point out. Yes, most of the studies are in the millivolts per second. It is actually in volts per second. So we are talking about a device which can be swept at 250 volts per second. It's not millivolts. It's not a typo. Yeah, thanks. That's the whole point of the work. So what is the physical interpretation of annealing the structure of CNT so that it yields high? Yes, so like I said, I think I've answered this question. What is the importance of annealing? What happens when we anneal? So from spectroscopy, I just wanted to answer it again. From spectroscopy, we see that both the one of the spectroscopic, one of the visual signatures that we get from Raman mapping is that the electrolyte actually, the annealing helps the electrolyte to infiltrate the electrode. That is one. Now, I didn't discuss about this, but we have done XPS of at the interface as well, X-ray photoelectron spectroscopy, which is given here. It is also given in the paper. So here, basically, what the annealing does is it creates carbonyl functional groups at the interface, and this actually assists in the seamless transfer of the seamless charge transfer across the interface, which is important for ultra fast capability. So I have a question regarding CNT. Says DK, gallium nitride has the advantage of variable band gap. Have you thought of doping CNTs with gallium nitride? Previously done, but not using solid state. I typically for this kind of applications we would want a zero band gap material or a material with a very low band gap. So I wouldn't probably venture into that direction. Manas, I think yeah, I've answered many of your questions. So Arjun Ajit is there a feed rate for the dip coating of the CNT thread? Yes, there is a feed rate. Is there an effect of the weaving pattern? Yes. Is there a dependence on temperature for lamination as there is the deformation of? Yeah, so we have to, there are certain tricks we can't do it at a usual temperature of lamination. We have to do it just around the glass transition or the softening temperature of PET sheet. So we can't, don't apply 200 degrees and then your electrolyte will burn off, will decompose. Okay, so Raman mapping for methyl cellulose ionic liquid is there after lamination or before? No, it's before lamination, because when you laminate, you essentially would not be able to look at the electrolyte. There will be a PET blocking layer. Sorry, PET blocking layer. So for the CNT yarn, is there any variability in the PVA sulfuric acid coating thickness? Yes, there is. Like I said, the optimal is about 150 microns. Anantraj, yeah, thank you for hi Anant. Two questions. In the very first GCD, you showed why the operating current density were 1.9. So because instead of integer numbers, because what we did was at the time we actually weigh the device, weigh the CNT thread, which is basically in the weight of a single CNT thread is going to be of the order of few milligrams or micrograms. So we don't have any fine control over the weight of the CNT thread which actually goes into the device. So ultimately, when you normalize it, it's very difficult to get it in terms of integral numbers. What we will end up with is fractions, because the weight of the CNT thread is something which is not under control. The same slide, you also showed the Nyquist plot for the device of different ratio of polymer ionic liquid. Depressed semicircle witnessed in the higher frequency regime is charge transfer. I learned that a capacitor in series with a resistor will give a line with no such semicircle in the Nyquist plot. No clear, no electron transfer. How come? So the in this case, what has happened in the semicircle that you see is basically will tell you the charge transfer resistance, or in terms of a Faraday process, it can also tell you it can also be correlated to the IR drop in case of a capacitive behavior, like what you see here. Okay, it's not an RCT, although it's technically called an RCT. We would more in supercapacitive terms, we would more prefer to call it as a IR drop or something. Yes. Please keep the aspect ratio. Yes, that's something which we always do. This is the impedance X and Y aspect ratios should be the same. I think we have just, if you look at the paper, we have done exactly the same thing. This is more to show you how exactly the semicircle plots. Sometimes we need to enlarge it in a non-proportionate way. The argument of interface being dissolved into one another at 80 degrees, that gives rise to more of interface, is not understandable. Okay, so when you see essentially, I'll try to explain it probably as the last question. Yes. So see, this is the spectral mapping, which shows that CNT is rich in one domain and the electrolyte is rich in another domain. Now, when you look at the same junction at 80 degrees centigrade, what happens is that you see that the electrolyte signature corresponding to blue in this map is seen not only on the outside but also on the inside. So that means the electrolyte has actually percolated, and this is because 80 degrees is roughly around the PVA sulfuric acid would soften down, and that would enable its diffusion into the CNT pores, and that's why we think that it's enabling us to access high rate capabilities. Nikita, why do you thought of using PVA sulfuric acid? Any other alternative? Yes, you can certainly consider many other alternatives. Just that we wanted to show as a proof of concept this picture. Can we have other stabilization like SCM, XRD? I'm not sure what that means. Sorry. Can you try? If you should probably try elaborating that question. Ayan Sarkar from ICER. Hi. Question: would you tell me how was the not annealed capacitor behaving like a resistor, and how they anneal? See, basically, when you have a capacitor and expose it to very high scan rates, there is complete breakdown of the double layer, and so it essentially would behave like a resistor. The C part of the RC circuit completely drops off, leaving behind the resistor, and that's why you get a linear, like ohmic kind of a behavior. Whereas for the annealed device, we see that there is still a cyclic voltammogram with a symmetric and supercapacitive nature, and that's why we think that it's a supercapacitor, and that basically happens because of the reasons which I discussed during my talk. Okay. How can I use CNT for optoelectronics? That's something. What about the thermal conductivity of the material? We are trying to measure it. There are a few challenges in measuring thermal conductivity. We are trying to do that. How can we increase the washable cycles? I don't think we need to really worry about that, because we have gone to about 20-25 cycles, and that is what ITRS demands. So I think we are pretty fine in that aspect. Tapas Das says, I was wondering the synthesis process of CNT in the wire form. What is the mechanism of formation? So what happens is you basically use a vertical CVD furnace. You put in the carbon source from top and the catalyst from the top, and then as it slowly comes down, there is a process of CNT formation, and it basically ends up like a aerosol kind of material, and then you start pulling it out. It's exactly like if you're seeing how the shopkeeper makes cotton candy. He puts in sugar cubes, heats it up, and then slowly winds it around the circumference. It's exactly the similar way that we use to draw out the wire from the growth chamber. Yeah, so I think we would. So what do I do, Dr. Diksha? So can I continue, or?
I think we can stop now. And okay. I think you must be tired. It has been like a lot of questions, quite a long some time.
Sanjog, hi Sanjog, how do you efficiently control or improve the surface area of CNTs? We'll discuss this when we meet sometime after the lockdown finishes. Yeah, please. Yeah.
Absolutely. So I think this has been quite engaging and quite insightful, intense session. People had like so many questions, 192 questions, and probably the highest number of attendee we had so far in all the series. So thank you for being so popular and having like so many people willing to come to listen your talk. And we had a very positive feedback as well in the comment section. Everyone found your talk very helpful, useful, and a lot of people are thanking you. So including that, we also thank you so much for taking out all these efforts and having such an interesting, engaging, and insightful talk.
Thank you.
I'm sure we all got benefited, and the attendees would want to hear you further, probably at another series or probably like an extension of that. That's what we are planning right now. Till then, we thank everyone, all the attendees, for their patience and being such a fantastic audiences, and grateful to you sparing your time and talking to people and then being as a speaker on our series. So with that, everyone, have a nice evening, have good dinner, and stay safe. And let's have like more talks and welcoming everyone to join our future talks.
Thank you. Thank you, the entire ACS team led by Dr. Deeksha. Wonderful opportunity, and I really enjoyed this session. Not only this session, the other sessions which I've been a part of, asking questions on the other end. So it's a extremely well thought out and well thought out initiative, and I'm thankful for giving me this opportunity. Thank you.
Thank you so much, and take care, everyone. Bye bye. Have a nice evening.